The final discrete probability distribution that we will explore is the hypergeometric. It is closely related to the binomial, with only two possible outcomes, but with one key difference. The trials are not independent, and the probability of success changes from trial to trial. Think of the example of dealing from a deck of cards, and we want to know the probability of dealing a heart or not a heart. That represents a typical binomial problem. If we deal out a card and put it back in the deck, when we deal another card, the probability of a heart remains the same for each trial. That's important for a binomial. But if we do not return that first card back to the deck, and then when we go to deal out another card, the probability of a heart has changed. There are fewer cards in the deck, and we don't know if we've taken out a heart or not. The way we can distinguish a hypergeometric problem from a binomial is that we have an indication that we are not replacing after each trial. The hypergeometric probability can be represented with a mathematical function. While it looks complicated, it's made up of something we have already learned, the combination formula. The input variables are defined here. Capital N is the number of elements in the original population. Small r is the number of successes in that original population. Small n is the number of trials, and x, again, is our variable of interest, the number of successes. A practical example to consider these inputs for a hypergeometric, again, could start with that deck of cards. If we consider a success to be a heart, there are capital N, 52 cards in the original deck, and there are small r, 13 hearts. We can deal out the cards without replacing and want to know the probability of X hearts. This diagram represents or describes the logic behind that formula for each of the three combination formulas. There are some limits to the application of the hypergeometric in relation to the values of R, N, and capital N. Now, for an example, using simple input values, something we may all have experienced when we mix up some good and bad items. In this case, capital N equal 4 batteries total on the table. R equals 2 of the 4 which are good. We select N equals 2 without replacement, and we're interested in knowing if X equal 2 are good. The mathematical problem is set up here. It's just a matter of inputting the correct values into the three separate combination formulas and solving with factorials. The mean and variance of a hypergeometric can also be calculated. Shown here for our example. This slide summarizes the properties of the hypergeometric distribution. When the population N is large, a hypergeometric can be approximated by a binomial distribution. While there are no convenient tables to calculate hypergeometric probabilities, Excel does have a function, hypgeom.dist, that can quickly calculate the results.